Okay.
All right. So this is a case study that utilizes all the stuff that we just learned in this chapter, right? So now we want to look at something in the real world and figure out how we can utilize what we learned in the textbook and apply it to a real example. So I'll start by showing you one of the machines again this was on. So again, the company I worked at was Unisig, made a lot of different machine tools. So this picture should show us pretty well. If you look at this, these are work pieces that come into the machine via this conveyor. And this is a W-axis, so it's a ball screw driven tailstock on this machine, and it rotates the parts. So this tailstock would move backwards or retract out of the way, and then the parts would come in and they would lift up, and then they'd be on center of these clamping fixtures, right? And then this ball screw would drive forward and clamp the parts together. So that's the application we're looking at. But if you have all these parts that are just cut to length, there can be a variation in the tolerance on that. So you need something to make up for that compliance, to add compliance to make up for that, that length difference in the parts. So we're going to look at an example just like this and figure out how we would design a system to allow for those different part lengths. So I guess think that you just got, you're working on this machine at a company and you're the design engineer, you get this problem handed to you and you have to kind of figure out how to solve the problem is a typical example. So what I would always do is start with the drawing of our situation, and that's kind of what's shown here. So we have the tailstock back here, which would move in and out to allow for the parts to enter the system. But then these clamping cones on the end are actually fixed in place. And then since the parts can be different length, we need some spring compliance. So that's where our springs are going to come into play. We'll have one spring on this spindle and one spring on this spindle. It's just showing a 2-spindle setup. Because if you only had one spindle, it might not be as much of a concern because you wouldn't have 2 different part lengths to deal with at the same time. Any questions on just the application or how we got to this? All right. So now we need to design the system and select a purchase spring for this. So these specific parts in this example, they could be plus or minus 3/8 of an inch. And the clamping force range that we want is 30 to 50 pounds. And the design is already set up so you can only use one spring on center of these spindles. So we want to provide all the info, the vendor info, spring lengths, rates, and the forces required. So I guess just similar to how Kelly was just doing, if you guys want to take a couple minutes and maybe think of some ways that you would approach this problem, like you're, in the real world, you get this problem, what am I going to do to try to solve this and select a spring? So I'll give you a few minutes to think through that, and then we'll talk about it. Is there any questions on it before you jump in?
Matter, like, because you gave us the difference, but does it matter how far the spring sticks off the other end?
No, you would just you'd want that to be within your working range of your spring. So you wouldn't want the spring fully extended to the free length or fully compressed to a solid length. You'd want it in between that. Right.
Noodle it over.
Do you want to keep it?
I can stop the recording or pause it for a little bit.
All right. Any ideas? I know it wasn't a lot of time, but any ideas on where to start with this? Go ahead.
The maximum K value.
Yep, K value, that's a good start. Any other thoughts? You guys all agree with that?
And when you talk K value, like spring rate, correct? Yes, spring rate.
Yeah, yep, that's.
How about virtually? Does anybody have anything to add virtually? Just want to give you guys a chance, make sure. Still awake? If not, that's okay too. Go ahead, Ryan.
All right, so yeah, K-value is something that we'll need to know for this. So what I always like to do is this your, how do you get to the screen?
That one right there.
This one?
Mhm.
All right, so I always like to start with our knowns, right? So if we look back at, whoops, this one,
That one.
okay. If we look back at here, we have a few knowns, right? We have part length difference, plus or minus 3/8, and we have a clamping force range. So we'll just list those out. So our part length is plus or minus 3/8 of an inch. That also equals 3/4 of an inch total. We have a clamp force range of 30 to 50 pounds. And we can only use one spring in this system. And we're looking to select a purchase spring. We want to select a purchase one. We don't want to make a custom one for this example if possible, right? Because it's lower cost. So what I always like to do to start solving a problem is draw a picture. And this will get us to what BJ was talking about the K value. But we got to figure out, we have these knowns up here, but how can we apply these to a calculation or an equation? So if we take a look back at our example here, we know a part length difference and we have these two known datums. So we can take that and create a more detailed sketch of that to try to understand what's going on there. So if we look at that top spindle, we have one clamping fixture there, and then in the bottom one, we have another clamping fixture here. Right, so we're just sketching that out. We know our difference between these two equals that workpiece part length difference, which is 3/4 of an inch. So now we have something to work with, right? If we know do we know there's springs inside of here? Right, like, how do you think this would look in this system? So this is the top spindle, this is the bottom spindle. And just based on like the examples you were looking at with the different install length, operating lengths, what do you think a spring setup would look like in here? Any ideas on that? Here, I'll give you an example here. On the back side of them? Yeah, yep, I'd agree with that. So you'd have a fixed point back here. If we take a look at this, it's real similar to this example, right? We have solid lengths, we have free lengths, installed and operating lengths. So whenever we're designing a spring, we want to be within that, within the free length, the solid length, so within that range, right? So if we apply that to this design, we would have a spring here, which goes back to a fixed point, and we'd have that same spring going to the same fixed point, right? And since this is compressed more, we know that's going to be our our operating force. And that's just based on this and the fact that if you compress a spring more, there's going to be a higher force. So that's going to be FO. And in this case, it would be 50 pounds because that's the max range that we're looking for. Any thoughts on what this one would be for the force? Yep. So we'd call this FI. It's our installed range. We don't want it to be our free length. Our free length of our spring would be farther out here. But since we're clamping parts within this range, we want it to be in that within the operating and installed. So the installed length is going to be our minimum value of 30 pounds. But we don't know the actual length of either of these yet. Right, those are still unknown. But we do know that the delta between them is 3/4 of an inch. So this actually would equal Li minus L, oops. Minus LO. Okay, so we have a max force, min force, and a delta. So now do you think there's an equation we could use to solve for an unknown variable here, like our spring rate or one of the lengths?
Well, after the A equals delta, by delta L.
Yeah, 18.1 A.
Yeah, 18.8. Yeah.
Yep, that one exactly, because we have Li, we have LO, and we have those forces, so we can solve now for our spring rate. So K equals FO minus FI divided by LI minus LO. So we have 50 minus 30 pounds. So again, we don't know Li. This is oh, that was right.
Yeah, hello.
No, that's not right. Should be LF and LI.
Well, no, it's just the delta between them. It can be whichever ones. It can be Li minus L. You were correct. Because it's up on the top one here, Ryan.
Okay.
It's that.
So we know Li minus LO equals 0.75 inches. So now we have our spring rate. Somebody wants to run those numbers, please. All right. And that's pounds per inch.
Did you say 26?
26, yeah, so sorry.
Okay.
It's okay.
All right, so now we have a spring rate. But now we need a spring. So I guess what I normally do is run some hand calcs like this and then put it into a spreadsheet if I'm going to be using this design criteria on multiple designs. So it's just easier to iterate on. So now if we take a look at that spreadsheet that's in your module. That's essentially what I created here is just a custom spreadsheet for this application. And this is real common in industry. You'll figure out, various equations and ways to solve a problem, and then you'll enter it into a simplified spreadsheet like this. So if you look here, you just have an example of what your situation is. And then some of the nomenclature described here as well, right out of the book. So for this example, we know Li minus Lo. That's also could be called our spring working range, is 3/4 of an inch. The installed force is 30 pounds. And the operated force is 50 pounds. So there's our desired spring rate that we just calculated. So you would just enter the equation we did by hand right into your calculator if you're creating this from scratch. But now we want to actually select a spring. So if you just go online and just look up compression springs, there's various vendors to choose from. So one I've used a lot is Lee Springs. So most of these vendor catalogs have nice filters on them to select your spring. So we're already on compression springs. But now there's various filters you can use. In our case, we know the spring rate. So we're between, let's just say 20 and 30 pounds. And we're on imperial and inches up here, so you can select your different units as well. So now they'll just give you a whole range of purchase parts to choose from, and you can sort by various parameters. So we're going to sort by our spring rate. Make the range up a little bit. So now we're just scrolling through here to try to find one that's close to our range.
A lot of springs.
There it is. All right, so here's all the 26.7. So there's a lot here to choose from and various lengths. So you can just look at that free length and try to find something that would work for your application. And the big thing here is you have a free length and solid length range that range needs to be greater than 3/4 of an inch. So that's one parameter you could narrow down to as well. So I'm going to go to one of the longer ones, like a 4-inch spring. Just so I know that I have enough solid height and free length to work with, enough of a working range.
And so what Ryan's getting at there is, yeah, the 4 minus whatever is the solid length, or the free length minus the solid length, that's gonna be your range of operating length, basically.
Right.
And you want that to be greater than the 3/4 that they need, that you can need for this example.
Right. So you could even use like a 2 1/4 for this one as well. So we'll select that part, 4 inches long. And 26.7 is the rate. So now we can just go back in here. Vendor is Lee Springs. Drop our part number in there. Free length and our solid length is 1.658. And And now these outputs will actually calculate our installed length, operating length, and the actual forces. So if our spring rate was a little off, we couldn't find the exact one, our forces might change a little bit. So you just want to make sure you're within the operating ranges of your system. And you also want to double check that your installed length and operating length, your installed length must be less than the free length, and the operating length must be greater than the solid length. So this is more of a manual check, just looking back at the spring you actually selected. This is a good diagram to always check. You're getting you're putting all these variables in here so you can check to make sure it makes sense. Any questions on that? Does that process kind of make sense? How to go from an application problem to a calculator that you could use on multiple problems?
Do you just want to go over the case study for their assignment real quick, as long as we're here? So if you go to the left
Sure.
slide. Yep, on that one. Yeah, let me go to the very last slide. That one right there. So maybe it's just kind of
Yes, so the case,
explain.
yeah, the case study here it's real similar, a different part length tolerance of plus or minus 1/4 inch. And the clamping force range is a little bit higher for just for larger parts. So 50 to 80 pounds would be required. But real similar, one spring setup. So utilize the spreadsheet if you can to solve for that. We already helped you out here. We put the second one in there. So this is something I've done a lot, is you just copy over all your column and insert a new one. So then you can run multiple designs on one sheet. All right, well, if there's no questions there, any questions online?
Okay. All right. Yeah, that's good. I'm really thankful that Ryan took time to make this example and then also relate it to something that he worked on in industry. He's and that's what's great about having somebody like Ryan here in our program, because he has come out of industry so recently, has some fresh examples of you know, how to apply this. And it just means a little bit more when you start going through that process. So thank you. Thank you. Thank you.
Problem.
So with that, that's the case study for that part of the homework. I'm going to back up and I'm going to go to the second to last slide. And the second to last slide is going to be our assignment number 8. So it's going to be these 5 problems and then the case study that you guys just went through, very similar too. So you'll have problem 2 and 4. Those are going to be similar to the first 2 practice problems we did. And then 10, 11, and 12 are going to be a continuation of problems 8 and 9. So we kind of set up these 3 here with those first 2, and you're going to use the information from 8 and 9 in your practice problems to finish out what they're asking for in problems 10, 11, and 12. So I think that kind of completes everything. Does anybody have any questions at the moment? Brandon?
So for the case study, or can we just do a screenshot of the calculation, or do we need to talk it through and kind of what, like, how to write it?
I'm gonna let Ryan decide. That's his problem.
I would say you want to at least draw a picture like I did. That's what I'd have my class do as well. So put the knowns down, draw the picture so it's clear. Otherwise, it's easy to get confused on what you're after.
Yeah. Yep. Great. And then any other questions? And then you can use a screenshot though of the calculations once you're done of the spreadsheet, because it's a little smaller.
Yeah.
It's not as big. Other questions? I do want to let you know that for 2, 4, 10, 11, and 12, my intent was for it to be hand calculations. So I do want to see the formatting that we use during our examples. So making sure you have your units in place, your variable, your equation in variable form, nice and easy, neat to read, okay, kind of follow through. And then making sure that your units are in your final answer, put a box around the final answer, okay? So, so that really concludes module number 8 then. So, so the rest of the time that we have today is yours to work. And then we're here for any questions that you might have. So